to this computer. Okay, let's do that. And now let's do screen share. Okay, so we're taking that same buffer that we calculated a while ago, and we're going to add some acid to it. Now, when the acid is added to it, let's see. And when the acid is added to it, we're going to use this same sort of equation, and the concentrations that we had from no, I'm sorry. Let's just skip that. When we add acid to a buffer that has nitrous acid in it and nitrite ion in it, the nitrite ion is the conjugate base. So the acid that we're going to put in will react with the nitrite ion. So this is the equilibrium that's set up. If we add acid to it, it'll react with a nitrite ion. And the reaction we're going to get is the proton transfer, Bronsted-Lowry acid-base reaction, to transfer the proton from the acid to the base to create this new acid and the conjugate base, of course, of hydrochloric acid, chloride ion. Now, this is not an equilibrium. So this reaction is, you can't have an acid and a base together unless they are reacting. Okay, so they will react with each other. And after the reaction's taken place, you're going to use up the 0.05 moles of the hydrochloric acid. So none of that's going to be present afterwards. But the number of moles of nitrite ion that you had was 0.28 moles per liter times 0.25 liters. That was 250 milliliters. And we had to multiply that together to get moles. And then we're going to subtract off the 0.05 moles of HCl that was added. And when you do that, you'll get the number of moles of the nitrite ion after the reaction has taken place would be 0.065 moles. The number of moles of nitric acid now would be the 0.45 times 0.25 you had to start with, plus the 0.05 moles that was made when this reaction took place in the solution. You created more nitric acid. So the number of moles you would have is 0.1175 moles of the HNO2. Now we need to plug these data in to do this calculation. So the pH is pKa plus the log of the nitrite ion, anion concentration, this one, divided by this one. Now the reason we're dividing by 0.25 here is that the Henderson-Hasselbalch equation is for molar concentration, not moles. In this case, you'll get the same answer because we're dividing the 0.065 by 0.25, and we're dividing the 0.1175 by 0.25. So if you divide those two out, this 0.25 and 0.25 cancels. And so in this particular case, you'd get the same result if you use moles or molarity. But be very, very careful. The equation is written for molarity. So the pH that we would get at this would be 2.89. And so if you look at this is the calculation worked out over here in a little bit more detail. But if you look at the increase in the decrease in the pH that took place, we went from 2.94 down to 2.89. It only made a difference of 0.05 pH units. So very little change took place at all when we added acid to that buffer. Now, let's do the same thing to the same buffer, but add base to it this time. Well, the equilibrium is still the same. This is the nitric acid, and there's the nitrite ion. we're adding base, so it's going to react with the acid, HNO2. And so the reaction is going to be the nitrous acid is going to react with hydroxide ion to make water and make nitrite ion. So the amount of nitrous acid is going to decrease, but the amount of the nitrite ion is going to increase when we carry out the reaction. So again, we have the same number, we have 0.28 times 0.25, that's the number of moles of nitrite ion. We're going to increase that by 0.005, the amount of base that we added here, and then that'll give us 0.075 moles of the nitrite ion after the reaction has taken place. But the moles of nitric acid, we had 0.45 times 0.25. That's the number of moles of nitric acid. But we're going to use up 0.005 in reacting with the 0.005 moles of hydroxide ion. And the new moles will be 0.1075. So if we do now our Henderson-Hasselbalch equation for this one, we've got 3.15 is the pKa of the acid that was given way back in an earlier problem. The moles of nitrite ion here is the 0.0075. Its concentration is 0.0075 divided by 0.25. The moles of nitrous acid that goes in the denominator is the 0.1075 divided by 0.25. Again, the 0.25s will cancel. You don't actually have to do this complex fraction because they all cancels out. And so when you do that, you get 2.99. Now, if you look at the this is the calculation done in a little more detail that you can see over in that little thumbnail that's on the bottom right-hand side of your screen. You can see that we got a new pH of 2.99. We added 0.05 moles of base, and we increased the pH again by 0.05 units. So again, adding either acid or base makes very little change, if any, to the to that buffer. Now, what if you added the same amount of HCl and NaOH to 250 milliliters of water? Well, if you added the hydrogen ion would be 0.005, and if you divide that by the volume, 0.25, the molar concentration of hydrogen ion would be 0.02. If you take the log of that, you get a pH of 1.70. So if you take 250 milliliters of buffer, you went from 2.94 way back there to 1.70 if you did the same thing to the buffer or to water. And you add NaOH to water, you add 0.005 moles of NaOH divided by 0.25, you get 0.02 molar concentration in hydroxide. We get the POH is again 1.70, but the pH is the difference between pKw and POH is 12.3. So going from the adding acid to adding base, we made a difference of pH of what? Just almost 11 units in going from acid to base. But the difference in the pH was 10.6 here in water, but the difference in the pH in the buffer was only 0.1 units. So I think this is a really powerful indicator of just how well buffers control the pH. It's only 0.94% as much as the change we made up here. And that's just in pH. Remember, pH is a logarithmic scale. So when you make a change of 10 to the 6 pH units, or 10.6 pH units, that's like 10 to that power in terms of concentration. So it is extremely large. Okay, we got one more topic to do, and I need to go back to my and pick up the acid-base titration part, and we'll talk about that, and then we'll finish them. That will finish the material that you'll have on your exam on Wednesday, and then if we have any time, we'll go on to the next unit. We don't want to lose any time that we don't have to. Now, when you're looking at a reaction, we're going to do titration curves during this. And really, there's only 4 points that you really need to consider. You need to know what the pH is before titration. Let's see if I can find a better marker. Before titration, get in here. That's the first point that we're going to be considering. And what you're going to have at that point is you're just going to have some weak acid, let's call it HA, and it's going to dissociate, and it's going to make H plus A minus. You're going to start out with some initial concentration of that, C0, none of that, and none of that. And then at equilibrium, you'd have C0 minus X, and you'd have X here and X here for the concentration of these two ions. And then the Ka is going to be X squared divided by C0 minus X. And the way we've done our successive approximations is cross multiply. You get X squared is equal to C0 minus X times Ka. And then we're going to say X is equal to plus the square root of C0 minus X times Ka. And this allows us to do successive approximations so that I can always solve for the initial concentration. So before any base is added, this is how you would get the pH. Now, if the acid has the same number of protons as hydroxide ions in the base, then at the equivalence point, what you're going to have is the volume of the acid times the volume of the base is the volume of base times the molarity of the acid. So volume of acid times molarity of acid will equal the volume of the base times the molarity of the base. So this is what happens when you start adding a base to this. So we're going to do other points like this. And what we're going to do is we're going to have the HA reacting with hydroxide ion. And what we're going to get is water and the acid anion like that. Now, anytime before the equivalence point, this would be the limiting reagent. And so it would all be used up. So it's going to become a buffer. When I put in some OH, I'm going to reduce the concentration of the HA. That's going to go down. And I'm going to increase the concentration of the A minus. That's going to go up. And I'm going to, before the equivalence point now, I'm going to be using the Henderson-Hasselbalch equation. pH is going to be equal to the pKa plus the log of the A minus concentration over the HA concentration. And you can go back to the examples that we've done a while ago when I added base to my nitrous acid and we calculated the pH. It works exactly like that. Now, what we're looking at is we're going to get a titration curve. We're going to put pH on this axis and volume of base on this axis. The first point on the curve is what we calculated for 0.1 up there. And then we're going to get a curve that looks like this. That's the way the pH is going to work. Now, this point here where you see this extreme increase, that's the point that we just did on the slide. This is the equivalence point. And at that point, the volume of acid times the molarity of the acid is going to equal the volume of the base times the molarity of the base. And we use that to analyze the solution to determine how much acid was present, since we're putting in a base of some known concentration. If we look at the volume of base it takes to get to the equivalent point times the molarity of the base, and we know the volume of acid we put in, we can calculate the molarity of our unknown acid from that equation. So this is going to be actually the third point we'll calculate a little later. And what we're doing right now is in this region here. And that's the region where we have a buffer. Now remember, as we add base, the pH doesn't change very much in a buffer region, not like it does over here. This is where we're getting close to the water value. We've almost neutralized the acid and base in a real strong acid, strong base calculation. This would be the neutral point, and that pH would be 7 at that point. And then the fourth point we'll tell you about in just a second is this limiting pH. So if I know this point and some points in here, or a point in here and a point here, and what the limit is, I can sketch that curve pretty well. So in this buffer region, you're going to get this. Now, there's a special point. If you look at this in this region, when I've added enough base to use up half of the acid, then the amount that remains is half of the A, and the amount of the half of the original HA, and the amount of the A minus I will get will also be half of the original HA. So these two concentrations will be equal to each other. So whenever the volume of base is equal to 1/2 the volume of base to get to the equivalence point, the pH is equal to the pKa. If this is equal to this, log of 1 is 0, pH is pKa. So there's a special point right in here, this one, that's fairly easy to get. This volume of base at this point is 1/2 volume up to the equivalence point. And this pH right here then is the pKa. So all during this region, we're going to calculate the Henderson-Hasselbalch value. And even if we did it at 1/2 the volume to titrate the base, we would come up with pH is pKa at that point. Now let's look at other points in the titration. The pH in that buffer region is titrated by calculating using the modified Henderson-Hasselbalch equation. Now I've modified it over here to show you what it would be in the case of just volumes. What we did in the previous problem, checkpoint problem, when we added base to a buffer, works the same way. I've just made it so it's a little bit easier to put it in to an equation using the volumes that we put in. So the pH is the pKa plus the log of the volume of base that you've added, divided by the difference between the volume of base it takes to get to the equivalence point, And going back over here to my camera, that's this point here, or this point that we calculate from the equation. Volume of acid times molarity of acid equals volume of base times molarity of base. So the pH is the pKa plus the log volume of acid, a base added, divided by the difference between the volume it takes to get the equivalence point and how much you've just now added. And this is the Henderson-Hasselbalch equation just modified for titration. Same thing, we could do it without that equation. Now, the equivalence point is the third point in our curve that we're interested in. Now, at this point, you're at the equivalence point. So when you're at the equivalence point, you have reacted all of the HA present. So the concentration of the HA before anything happens would be equal to 0, and the concentration of the A minus, now that's going to be, all of the HA is going to be converted, but you have to watch this. The concentration of A at the equivalence point is not going to be the same as the concentration of the HA you started out, because you added base all the time. So so the concentration of the A minus is going to be the volume of the acid that you started out with divided by the volume of the acid plus the volume of the base to get to the equivalence point. This is the new volume. So this is a dilution problem. You take a concentration in that many moles of that concentration and you dilute it to this new volume. That will give you your new concentration. So the A minus then is starting out at this concentration, but it's going to undergo a dissociation. So what's going to happen is the A minus now is going to hydrolyze, and it's going to react with water, and it's going to go into an equilibrium of HA and OH minus. So at the equivalence point, you're going to start out with some concentration of this. I'm going to call it C0 again, but remember, this is going to be the C0. It's the concentration of the anion we started with. We would have had none of this or this before the equilibrium. After the equilibrium, you're going to have X and C0 minus X. So when we get to the very bottom line, we'll get a derivation just like we did up here. It'll look just like this one, except what we're going to get is, in this case, our OH minus concentration is going to be equal to our X, and that's going to be equal to plus the square root of C0. I'm going to put a little prime on that to mean, don't forget to dilute that. You know, you got to dilute it. C0 minus X times the constant now is KB. That's going to be KW divided by the Ka of the acid that we started out with. So this is going to be what we'll get over here when we determine this. So you're going to have the hydrolysis of the anion and dilution to get to the equivalence point. So now, if we did this problem, remember what you're going to get here is you're going to get POH, because the X in this is the OH minus. And when you get that answer, you'd have to then take the pH to be equal 14 minus the POH. And I'll remind you here, this has to be greater than 7. because anion hydrolysis produces a base. So when that anion hydrolyzes, it produces a base. So the pH at the equivalence point is going to be actually greater than 7 for weak acids. Okay. Now, now when you get to a large excess of the titrant, let's go back and look at what we have now for our 4 points on our scale. This one was number 1. And this is the volume of base down here. And we had this 0.2. The one that we calculated was pKa at V equal 1/2 V to the equivalence point. And this was the distance, this was the volume to the equivalence point. Okay, so say if it took 30 milliliters to reach the equivalence point, you'd go back and read your pH at 15. And that pH would be the pKa of the acid. And in fact, that is a way to get the pKa's for acids that we had, you know, way back when we had our handy dandy rinky dinky little acidity table. Okay, that's how we get those numbers. Okay, so now let's think about logically what you get. What would be the logical highest pH you could reach? Well, what are you doing? You're adding sodium hydroxide at some concentration. So this pH 4 is going to be the pH, number 4 is going to be the pH of the NaOH. Let's say we've added in this acid-base titration. So if you just look at, if you titrated, say with, let's just suppose the molarity of NaOH that you're using as a titrant was equal to 0.15 molar. Then what you would do is you'd say, okay, the OH minus concentration in the titrant was 0.15 molar. The POH would equal to, let's see what we get, minus the log of 0.15 is 0.82, and then the pH would be equal to 14 minus POH, 0.82, and 14 minus that answer is 13.18. Okay. So there is the, that is the 4th of the points. So our titration, we know how to calculate these 4 points. Now you really ought to know this, because if you can do these 4 points, you can actually then sketch through those points to get the what the titration looks like.
Can you move your sheet up a bit?
I'm sorry?
Can you move your paper up just a smidge? Thank you.
Okay, yeah.
Yes, sir.
Okay, very good. I pushed it up while I was writing. Sorry about that. Okay, all righty. I couldn't log my laptop in, so I can't see exactly what you're seeing. Okay. Okay. Now, I want to distinguish 2 words for you. One is the end point in a titration and the equivalence point in a titration. The equivalence point in the titration is what we got right here for number 3. That is the pH when you have added equivalent numbers of moles of acid and base when you're doing the titration. Now, how would you know that? Well, perhaps if you had a pH meter, you could look at it like that and follow it along and see where you get that big jump. I didn't mention it, but you could go from about this point right here at the bottom of that curve up here to the top of that curve in about 2 drops of your base. So when I talk about that being a steep rise, that is a big high jump that takes place at the equivalence point. Now, how would you know that? Well, what we're going to have to do is we have to use an indicator. And the indicator, let's suppose the indicator I put in right here and maybe right here. This might be an indicator. It's in one color when its pH is this value. It's in the other color when its pH is this value. So that might be like phenolphthalein. Phenolphthalein is colorless when it's acid. So if you're adding base all along here, you don't see any color at all until you get, as you get real close to this, what will happen is you put in a drop of the base and it will form the pink color right where the drop hits, but then it dissipates and disappears. That means it's still got your acid in there to react with it, with that indicator color. Now, when you get past the equivalence point, the next drop you add is going to jump you up into this region of the base color. So for phenolphthalein, that occurs roughly at pH 9 for phenolphthalein. So you'll be going along and maybe you're looking for a pH of 7.8 or something like that is the equivalence point pH. Well, phenolphthalein won't exactly hit that. It'll change colors at about 9, but there's such a little volume here, it doesn't make enough difference to worry about in most cases. But ideally, the end point is the place where your indicator tells you you're done. It goes from the acid color to its base color. And we've got a whole host of acids and bases that we could use. The book does a real good discussion on picking an indicator for titrations. It's more than we need to worry about here. In your labs, the only thing you're going to see is phenolphthalein probably. But if we could find an indicator that changed color, say my equivalence point pH is 7.3, if I could find an indicator that had a pKa of 7.3, then that would be a great indicator to use. The indicators are acid bases that are just colored one color in acid and a different color in base. Okay, and the end point is when the indicator changes color. So hopefully they'd be close together, but they're not exactly the same unless you pick a good indicator. Now, you want the indicator to be about the same as the pH of your titration. I think these problems are all pretty good, but I'll click through them quickly with you. 50 milliliters of 0.049 molar HCl is titrated with 0.075 molar NaOH. What's the pH before any acid is added? Well, this is a strong acid, so all of the acid is present as hydrogen ion. So its concentration is the same as the acid, and so we get pH of 1.31. What's the pH after a milliliter of the base has been added? Well, the reaction is this is the reaction you're taking place. You've got 50 milliliters of 0.049 molar of this, and you had 1 milliliter of 0.075 molar of this. The base is going to be used up because I got 2.40 millimoles of acid, and I'm putting in only 0.075 millimoles of base. After the reaction's over, there's none of this left. So what's going to happen is this is going to now have dropped its concentration, so I'm going to have 2.40 millimoles, and now it's in 51 milliliters. So I solve for the new molarity, solve for the new pH. So it goes from 1.31 to 1.33 when I add 1 milliliter of base. After you added 16.5 milliliters of base, well, you'll see why that is in a minute. We had 50 at 0.049. We put in 16.5 at 0.075 molar base. Take that number of millimoles, subtract it from that, you get 1.2375 of this, none of that. So the hydrogen ion concentration is that many millimoles in, again, 50 plus the amount we added was 16.5, so 66.5 milliliters, 0.0186, and the pH is 1.73. So we're going along, we've not changed the pH a lot in this strong acid, strong base titration at all. Now, at the equivalence point, well, you got a strong acid and a strong base. It's just water. So you've got at the equivalence point, its pH is neutral, 7.0. When you had 34 milliliters of base added, well, here we go. The 33 milliliters of base was what it took to get to the equivalence point. So we've added 1 more milliliter of base past the equivalence point. And so what you're going to have is 0.075 millimoles of hydroxide present. The acid is all gone. And that gives us 0.075 millimoles in 84 milliliters, the 50 milliliters we started out plus 34. The OH minus concentration is this value. The OH is 3.05, negative log of that. And the pH is 10.95. So 1 milliliter of base takes you from 7 to almost 11. So that's why I told you 4 pH units in 1 milliliter. So that's a really fast jump that occurs there. When you add 50 milliliters of base, now you've used up the acid. No, I'm sorry, you haven't either. You've got an excess of this because they weren't at the same concentration. So your OH concentration is going to be now recalculated to that value. pH is 1.8, POH is 1.89, pH is 12.11. Again, we went by about a pH unit when we made that change in concentration. Okay, now, if we did the same thing with this, with the nitrous acid example, before any was added, we would do our calculation like we did before. We would get the hydrogen ion concentration. This pH would be 2.25 to start out with the weak acid base. Notice the weak acid has a higher pH than the HCl did. It's supposed to. It's a weak acid. Okay, and then what is the pH after 1 milliliter base is added to this one? Well, we're going to use the Henderson-Hasselbalch equation. I put in this one, and we had 33 milliliters required to reach the equivalence point. So the pKa is 3.15, so the pH is 1 milliliter of base divided by 33 minus 1. That would be an approximation, but we get 1.64. So that would be the pH after you've added a milliliter of base. So you didn't go up very much here either. Okay, now we can plug in our data for the Henderson-Hasselbalch equation and get an exact value if we included these two terms. We're not going to do that, but I wanted to show you that it is an approximation when we do things, just ignoring all the equilibria that's involved. So this is what you would get if you put in these values and then did successive approximations to get your hydrogen ion concentration. Okay. When you add 16.5 milliliters, well, we know what that's going to do. 16.5 divided by 33 minus 16.5 is going to give you, again, 3.15. Okay. If we did the exact calculation is 3.18. So you see, it's not bad when we get out here a little further away from volume 0. The approximation gets better. Again, I'm just showing you the result, but you should know how to do the approximation like we've done up here. And equivalence point pH, we've got that many milliliters of that molar over a total of 83, actually at the equivalence point. So this is our concentration minus X, and X and X. X squared over that concentration minus X is Kw over Ka. We do the calculation, approximations, you get 6.481 times 10 negative 7th, and the pH is 7.81 is what you would get. If you add 34 milliliters of base, pH is 10.95. And when you add 50 milliliters of base, you get 12.1. Now, so you have to do, if you do that with ammonia or any others, you can practice some examples like this to show how you could do the calculation. The only thing that's different now, this is an ammonia is titrated with HCl. So you can expect, you know what the titration is going to look like. If I plot pH in this case against volume of HCl, well, it's going to start out as a basic solution. You know, pH 7 would be down here somewhere. So it's going to start out, and it's just going to invert the curve that we had up there. It's going to look just exactly like before. This would be our new 0.1. Our new 0.2 would be, this would be the equivalence point volume. And then half of that equivalence point volume would be the pKb of the base NH3. And this would be our 0.3, and then this would be our 0.4, the pH of the HCl that you're using to titrate it. So it's going to look just like that. It's just that most of the time you'll be working with pKb and so forth. Okay. All right. Checkpoint on here again. Pull it up and go to the to D2L discussion, and we can do our work there. Okay. Let's go back to screen, and now let's see if you have any questions now about the practice quiz. Are we good? Okie dokie. Then let's begin segment 8, and we'll put the PowerPoint up for that, and I will now go back to screen share. Okay, now I know you might have been reluctant to ask me questions about that practice quiz, but again, if you will go back to, I tell you what I'm going to do. I'm going to do some things to it a little bit later. I'm going to put a Dropbox up. That'll make it easy for you to just say you've got a problem you're working on and you don't know how to do it. Take a screen picture of it and put it in my Dropbox. I'll put it in the Dropbox for the course, and periodically I'll go in there and look, see what's there, and I'll answer your questions in by email. But be sure that you put your name on that so I know who it is. If D2L doesn't do that automatically, I don't know. I haven't used a Dropbox before. So again, I'm learning probably slower than you are, but I'm learning to try to use this way of presenting the course. Now, we're going to look at another kind of equilibrium in this unit. Eventually, what we're looking at is going to be the solid liquid equilibrium, or you remember we gave you some rules about solubility rules back in Gen Chem 1.
Can I
Yes,
ask a question really quick?
sure.
Not pertaining to this information. If I have another class for a Zoom meeting, is it okay if I leave this meeting to join that one?
Oh, I am so sorry. I'm way over. Okay. No, I was looking at my time wrong. You're very right. Of course, to leave the meeting immediately, and I'll drop it, and I'll pick up with the very beginning of this after their quiz on Wednesday. I'm so sorry.
Okay,
I
thank
didn't
you.
see it.
Oh, you're fine. I'm sorry.
Yeah, well, no, any of you guys that happen to be in a meeting, if I go over, just tell me and I'll stop. Next time I'll have a watch out here that I can look at more closely. So this will be the end, and I'll see you guys then on Wednesday.